go from current slide. And I don't know what's going on, but it may be my computer. It did this in the last class too. And I thought it was a chord in the last class, because this has been doing so well in here. And there it is. Okay. I can't make any sense out of it. Okay. Before I make any announcements, I'm going to see if I can wait until at least Jake and maybe Jalen come in, because they typically both come in a little bit later. But when they both get here, then I'll go back over the stuff that we need to talk about to end our class. So let's go on and get started with trig. We're going to do the last example, example 10 in 6.3. We'll do it here and then pick up and go from there. But first, any questions on anything we've done so far, how we're going to end things? And again, I'll talk about that when the others get here, if any more get here. Any questions? All right. Here's example 10, page 423. Chapter 6, by the way, is additional topics in trigonometry. 6.3 is vectors in the plane. And this is the last example. No, there's two more, 10 and 11, but neither one were on the slide set. So I think we got started on this one, but I think we ran out of time before we got too far. Here's what our deal is. And get used to this, because most of you are going to take physics. And when you take physics, you're going to be doing problems just like this. Okay? Here we have a boat ramp. Okay? It's not a very steep boat ramp. It's 15-degree slope. Okay? And you have the boat, and I don't draw boats well, but just pretend this is a boat here on the ramp, and you're hauling this up with a truck or something, and you're pulling on this up the ramp. A force of 600 pounds is required to pull a boat and trailer up a ramp inclined at 15 degrees from the horizontal. Okay? So here is a 600-pound force. Okay? That is your force up the ramp. Okay? 600 pounds. That's a vector quantity, by the way. Find the combined weight of the boat and the trailer. Ugh. How in the world would we do that? Okay? Well, here's how. We break the components of the forces down. Okay? The ramp is pushing up at the boat with what we call a normal force. Okay? And that means that the boat is pushing down on the ramp with a normal force. Okay? That's Newton's third law of equal and opposite reactions. Okay. The actual weight downward is straight down. Okay? And this is what we're looking for. You want to give that a name? And we'll name it Jake. Okay. No, that was something else. Okay, once upon a time I had a pen. There it is. Jake's here. Okay. All right. Still missing Gavin, Josh, and Jalen. Okay. All right. Want to give that a name? The weight of the boat and trailer? Would W work for you? Okay, let's call it W. And by the way, that is also a force. Okay? This is the weight downward. Okay, now this weight downward is broken into two components. One is the component of the force up the ramp, okay? And the other is the component of the normal force perpendicular to the ramp, which makes a right angle. All right, you through? It's only if I see something wrong here, but right in the start, got quick, I can give you part of that. It's up to you. Okay. It's up to you. Okay. Now, is that sort of making sense? Okay. So you have the weight downward, that's this component here. That's what we're looking for. This is the unknown. Here is the force up the ramp, and that's our force of 600 pounds. Okay. Now the question here is, what angle is this one? We know that's the right angle. So do we know anything about either one of those two angles? Okay. Well, yes.
One at the tip is 15 degrees.
Okay, very good. And here's how you can determine that for sure. Because this is perpendicular to, this is straight down, there's your horizontal, that's vertical. That's also a 90-degree angle, okay? And this angle up here, that's the same as that one. You know, that's in the same direction as that. So therefore, I can say this right. This angle here, because this one and that one add to be 90, obviously, right? Well, this one and that one had to be 90 because that's the perpendicular. So therefore, this angle has to be the same as this, which is 15 degrees. So you're absolutely right. And you can do that by similar triangles, okay? So here we have, this is also our 15 degrees, okay? Now, do you see a trig function that relates this angle to this side and that, which is, by the way, your hypotenuse, because that's opposite the right angle. Any trig functions that relate this angle to this side and the hypotenuse. Sine, because it's the opposite side here. And we know what that is. That's your 600 pounds. So we know that the sine of 15 degrees is equal to the opposite side, 600, divided by W, the hypotenuse. Which means what? We're looking for W. There it is. Okay. What can you do to get W? Yeah, multiply both sides of the equation by W, get it out of the denominator, okay? And then we're trying to isolate the W. Divide both sides by sine of 15 degrees. All right, so now those go away. So W is equal to 600 divided by the sine of 15 degrees. Okay, be sure you're in what mode? Degree mode. Do the math. Okay, let's just leave it there, pounds. That is the total weight of the boat and trailer, okay, by direct trig calculation. Had nothing, well, it did have something to do with vectors, but practical application, you'll see this kind of problem beaucoup times in physics class, okay? Any of you had? No, you probably wouldn't have had physics yet. All right, so that was example 10. Any questions on that? There is a checkpoint following it, so if you need a little more practice on that, please do the checkpoint. Preferably soon after class so you can get that done. Get it in your head while it's familiar to you. So let's go to example 11. So I'm going to clear my ink here and start back over. Okay. An airplane travels at a speed of 500 miles per hour with a bearing of 330 degrees at a fixed altitude with negligible wind velocity, as shown in figure 24A. Okay? So let me reproduce figure 24A. 624A. Okay. Here is north. Of course, that would be south. This would be east. And this would be west. Okay, and when they say the plane has a bearing of 330 degrees, that's taken from due north. Now we're no longer using positive horizontal axis. We go up from due north. 330 degrees, starting from here, going counterclockwise direction. How far do we go? In the what quadrant? Second? Third? That's where I stopped it. Is that where we really are? This would be 90, 180, 270. I got some more ways to go, don't I? Good deal. Is anyone left in the room? Huh? You're the last one. Okay, thank you so much. Okay. So we'll go where? Okay, 60 past this one, so that's going to be up here, which means we have 30 left. 330 from 360, yeah. So we have 30 degrees left here, 60 degrees here. Yeah, you got the general idea. So this is the plane's bearing, and he's going at 500, wasn't it, miles per hour. So that's the magnitude of the vector at that angle, m miles per hour, okay? All right, a bearing of 330 at fixed altitude with negligible wind velocity, as shown in the figure. Note that a bearing of 330 corresponds to the direction angle of 120 degrees. That's if you use the positive x-axis, okay? That would be 90 plus 30 is 120, okay? The airplane encounters a wind with a velocity of 70 miles per hour in the direction of north 45 east. So north, you look to the north, then go 45 degrees toward the east. So here is your wind, okay? I'm going to call that WD for wind, so you don't confuse it with west or something, okay? And that's 70 miles per hour. So the magnitude here is 70 miles per hour, okay? And it's 45 degrees east of north. What are the resultant speed and true direction of the airplane? So what are we doing here? What are we doing here? Yeah, and how do we do that? Okay, and how do we do that?
You have to have the points from the vector.
Okay, if what you mean is components, is that what you were saying?
Yeah.
Yeah. And we do vector addition. That's what we're doing. So basically, we're adding this 70 at 45-degree angle here. I don't know if I have the length right. This is 500, that's 70. That's a good deal less than 1/3 of the length. Something like this. This is 70, magnitude of 70 miles per hour. And the angle here is 45 degrees. Okay? So, two ways you could try to do it. Okay? One is try to scale it correctly and do vector addition with geometrically. Not my choice, by a long shot. So the other would be to use your components. So let's first determine the components of this vector here in this plane here, okay? And we can do that fairly easily because those are some of our favorite angles, 30s and 60s, okay? So what would be the component for that, the plane's bearing and direction? How would you determine that? There's several approaches you can do. Tell me which one you would do.
So the magnitude
Yeah.
would be the I think a 500 miles.
That's the 500. You're absolutely right.
And then would you use 330 degrees or 120 degrees? That's the direction.
Okay. Depends on you. Frankly, the 120 to me is pretty easy to use. That's going to take care of the sine and the SIG and sign. So what do you do with that 120 degrees? That's the angle from here to there. Okay. That's your 120 degrees. I'm going to do this in a different color. Tell me what color you want.
Red.
Red. Okay. So that's your 120 degrees there. Okay. How are you going to determine your components for that airplane vector using the 120 degrees?
Just add it to 120.
Did you say that one more time?
Or you just add 70 to 120.
No, 70 is measuring the magnitude of another vector. 120 is the angle of another vector. Angles and magnitudes don't add. They have to be the same thing. Miles per hour or degrees or whatever, but you can't. Let's just forget about this one for now. Let's just do the components of this one. You have an X component and a Y component. Y component, X component, however you want to do that. Okay. Now, to make it easy on yourself, if you remember, I don't have the slide, so I can't go to it, but I'll point you to it in the text. I know it's in here, I just can't see it. Direction angles, there it is. It was on the very page I started looking at. Okay? Yes, sir. Oh. My hearing's so bad, I can't really see. Right. That's why I wanted to look across that to sky. Yeah. Okay. So you're going to end like this? Well, I mean, if this is what you're gonna do, that's fine. That's what I'm asking.
Thank you so much.
I'm sorry?
I said thank you so much.
Okay, sure. Okay. All right. It's what they call in the text the direction angles, okay? And
So just
yeah,
find the cosine and sine of 120 degrees.
exactly. And which one corresponds to what?
So the cosine's to x and the sine's
Yes,
to y.
exactly. So the x component, and I just find it easier to name these things. Let's call this the airplane vector, A. Okay, and this will be the wind vector, W. Is that okay? Or P vector for plane, or whatever you want to call it. Okay, so the airplane vector is going to be its magnitude, which is 500 miles per hour, okay, times the x component is going to be times cosine theta. So this is airplane vector x component. So I think I'll take off the vector symbol since I'm just doing with a component and just say a sub x. And the reason I hesitate there, because quite often in physics that's acceleration, but this is not. This is airplane vector, okay, times the cosine of theta, and that theta is, of course, our 120 degrees, if I can find my thing again. So let me just go and write in that 120 degrees, okay? And your a sub y would then be what? Help me, somebody. 500 miles per hour times the sine of 120 degrees. Now, you tell me what you expect the answers to be. What would be the SIGN signs of this vector? X component?
The sine is going to be negative.
Second.
Sine's going to be negative.
Negative, and the Y component?
Sine's going to be positive and the cosine's going to be negative.
Yeah, but, okay. But the SIGN sign of the X component is going to be negative, Y component positive. And that's because, like you said, cosine is going to be negative, sine is going to be positive. Yes, that works. So you tell me what those components are. A sub x is? And both of them less than 500 miles per hour, guaranteed.
A sub x is negative 250.
Okay, I couldn't hear that.
Negative 250.
Negative 250?
Yeah.
Okay. We could have done that, couldn't we? And that's miles per hour. And the y component? $433 miles per hour, and that's positive. Okay, so that's basically your coordinates here, minus 250, comma 433. I'm leaving off the units. Okay, now let's do the same for our wind vector here, which I call W. Okay, and the magnitude of that is 70 miles per hour. And if you do its directional vector here, that would be, how many would that be? No, okay, 70 miles per hour is the magnitude.
Yeah, 70 miles per hour times the sine or cosine of 45.
45, so that angle is 45 degrees, okay? So let me go back to, it doesn't matter. I could have, I'll go back to black there, here. Okay, so the win sub x is, like you said, 70 times the cosine of 45 degrees, and the win sub y is 70 times the sine of 45 degrees. And what do you expect out of these two?
The x and y values will be positive.
Both positive. And what else?
Parallel.
Well, equal to, that's the equal sign. Equal to each other, because 45 degrees sine and cosine are the same. Okay? So just calculate one, I don't care which one, and it'll be the same as the other. What would that be?
$49.5.
49.5 miles per hour, and this one, I bet you, will be 49.5 miles per hour. So, and they're both positive, so to get the, how did it ask for it? I'm on the wrong page here. What are the resultant speed and the true direction of the airplane? Well, I'm going to get the true direction first, okay? So let's do that first. How do you do that? Add the components. So the, let's see, let's call this T for true direction. Is that okay? T sub x is going to be minus 250 plus 49.5. I can't write well, okay? Somehow I got an extra dot in there. Okay, and that gives us approximately minus 201.5, 200.5, isn't it? Okay, and T sub y would be got it, 482.5. Okay, so those are the components. What do we do with them? What are we looking for? Right. The magnitude will give us the speed of the plane, because we're looking for what are the resultant speed if we find the magnitude of those two components combined. And I'm just going to draw them. What color you want the resultant to be? Green. Light or dark? Dark. Okay. We'll have this being our resultant vector. Okay. And we'll call that the vector T. Okay. So the magnitude of T is going to be what? Okay, and pull out your handy dandy calculators and see what that resultant speed will be. The magnitude of the velocity vector, the overall total velocity vector. I would guess a little bit greater than 500, but not a huge amount greater than 500. Okay, let's just call it 523. So the magnitude of this would be about 523. Is that what you said?
Yeah.
I can't write. That's miles per hour, because you don't have just not only the propulsion of the plane, but then also the little bit of wind behind it. Okay? And then how do we get the, as they say here, the true direction of the airplane?
Is that when you're trying to find the degree?
Okay? Of what?
The angle T for the
Yeah, the angle here. Now, how do you want to measure that? The original bearing they gave us was from true north, so it would be around here. Remember, that was our 330. So this is either going to be all the way around to there, or we can go back and do the one from here. It's up to you. Which way would you like to try?
Just do it from the horizontal.
I think that would be the easiest, okay? And how do we get that? I'll do that in green too. I think I'm still in green. So we're looking for this bearing right here. That is the unknown. And then we'll adjust it to be what the problem's looking for. How do we get that? Somebody help me. How do you get that?
Did you?
What?
You do 45 minus 120.
Okay. Because these are different lengths here, that this skews that way in favor of this one. So no, we don't have that. Okay? Now, how about using these two numbers we got here? Piece of X and piece of Y. What's their relation to bearing?
That's the trigonometric values, sine, cosine.
Okay? All right. The values we got from the sine and the cosine, and I think you're really close to it now, especially since we know the total magnitude, 523. So I think what we could do is basically the good old thing of rise over run, right? Your rise is your y value, which is this one. Your run is the x value, which is that one. And if you fiddle with that, that gives you the slope, which is the tangent of an angle. Now, it depends on which way you do it and what signs you use and stuff, you can determine. That's why I said which one do you want to do here. Frankly, in my book, I would probably go with the reference angle here, okay? And the rise and run and, adapt for the signs there, SIGN signs. Just do magnitude, this, that, rise being this, run being that. And the tangent of this angle is going to be the rise over the run. But it's also going to be the tangent of this angle, rise over run. But then you use the signs in it. But you still may not get exactly the right number. So which one do you want to try? I don't care.
The reference angle.
Yeah, let's do the reference angle. Okay? So let's call that, do you want to do a different color for the reference angle? Or you want to do it green? Huh? Blue. Light or dark? Dark. Okay. So we're going to use this reference angle here. Okay, we'll call it theta sub r. And what I just said is the tangent of theta r, and here we don't use the SIGN signs. We just use the magnitudes. That would be rise over run, so that would be 482.5, just because you gave me that many digits. Why is that not writing? I don't know. Okay. Over magnitude here was 200.5, just the magnitude. Okay. All right. Goodness gracious, this thing is aggravating. All right. Where do you go from there? What does that give you? Inverse tangent. Do that fraction, then do an inverse tangent of that, and see what you get. Or you can just do inverse tangent of that fractional form. See what it gives you. What does it give you? Frankly, to me, looks like something greater than 60, but less than 90. What do you get?
Wasn't the 200.5 a negative?
Okay. For the reference angle, we're just using the positive values there. What do you get?
I got, put 200.5 as a negative, so I got negative 67.4.
Okay. I don't have a calculator. Let me see this. Let's just do 482.5 divided by 200.5. Yeah, that sounds right. That's 67. That theta r, the reference angle, is 67. And tell me what that would be. 67 what? Point what? 0.43. Let's just leave it at 67 degrees, approximately 67 degrees. All right, I'm happy with that. Okay. Now, let me mark Jalen here before I forget it. Okay. Okay, we've got everybody here except Gavin and Josh. Okay, so I think I'll go on and make my announcements after we finish this problem. This is example 11 on page 424. Okay, now, how do you want to describe, we got the reference angle, how do you want to describe the, what do they call it, the true direction of the airplane?
So it would be north 67 degrees west.
Okay, no, okay. You see, north, so many degrees west, that's this angle, not that. That's why it was important to identify which angle we're talking about. But how is this angle related to that angle? Complementary angles to each other, right? Because they add to 90. So subtract that from 90, subtract this from 90, and what do you get? About 23 degrees. So I think the answer is, I'm going to go back to black here, your theta true, for lack of any other way to name it, would be, as you were saying, north, what did I say, 23 degrees west. That's the actual, what do they call it, true direction of the airplane. Okay? Of course, that's not how they say it. They use the angle over here, the green angle there, and how would you get that from 67 degrees? they use this one. Part of the relationship between our 67 here and the green angle there. Supplementary angle. So you subtract this from 180, and that would give you 113, I think, wouldn't it? Something approximately like that. So if you use that one, the theta total would be 100. What did I say? 13? I believe that was right. 113 degrees. That I would never have used. Okay? Okay, and they got 112.56. Okay? Now here's where I said before. If you go back to the very beginning, we used the angle that was all the way around like this. And I think that's also the one they give you in the book. So if you take our 23 degrees and subtract it from 360, that would give you a theta total. Depends on what you're measuring from. Okay. 180 minus 23 would be 157. No, 357. Yeah, 357 degrees, approximately. That is from 337. I'm sorry, I can't subtract. Yeah, that would be 3 degrees short. 337. Subtract from 360. 23 from 360. Yeah, 337 degrees. That's the one I think they used in the book, because that's the one they gave you to begin with. They said this was 330 degrees here, so it'd be 337 degrees there. As long as you identify what you're measuring from, those are fine. If you say the North 23 West is perfectly fine, but that's what they gave wind speed by, not the direction of the airplane. The 113 you'd have to really describe from due east, counterclockwise from due counterclockwise from due east, and that would be 113, or what they said from the beginning, airplane travels with a bearing of, and the bearing is from true north, that'd be 337 degrees. So just 23 degrees short due north. All right, so you just have to identify what you're measuring from. All those are correct answers if you say how you're getting them. Okay. All right. Any final questions on that? Before we get into the vocabulary here, let's go over our end game here. All right. Let's start with this. I've received, as far as I know, 3, and only 3 papers out of the 1, 2, 3, 4, 5, 6, 7, 8, 9 students in the class. That's 1/3 of the class has turned in a paper, and you have one more class period to turn it in. Okay, so please, folks, get your paper in by Thursday. Sooner the better. That gives me a little more time to flexibility in grading it, but please get it to me as soon as you can. Okay. First test, I've got 1, 2, 3, 4, 5, 6 out of the 9, so 2/3 of the first test are in, unless someone's given me one real recently. Second test, only 2/9 have come in. 2 of the 9 people have turned that in. The third test you've had a little while now, and I've received 0 of those in. Okay. Now, what's going to happen on Thursday, I'm going to return all those papers to you, meaning I can't receive any more after Thursday. Okay. So please, folks, get me those tests before class on Thursday. Okay. And then at the end of class on Thursday, I will give you 2 tests, actually, both very short and hopefully very sweet. And they will be one on chapter 6 and one that's comprehensive, okay? Covering all 4 tests, all 3 chapters that we've covered, and only what we covered by the end of class on Thursday. So more than likely, I'm going to have a few questions on there that may turn out being bonus questions if we didn't get them covered, because I have to make out the test before class, okay? So any questions on that? So please get me your research papers and all your tests to me by the beginning of class on Thursday. Clear? Yes.
So those that you're giving us, that's the final?
Okay. The 2 tests. One will be the 4th test, test 4. The second will be the comprehensive final exam.
Okay.
The comprehensive final exam cannot be dropped, and the research paper cannot be dropped. Other than that, I will drop your lowest test score if it helps your average. If you really bomb the paper or bomb the final, then you probably need all your test scores to bring that up. So
When
I
do we
don't.
need to turn the final in?
What's that? Oh, okay. Yeah, good question. Let me ask this before I answer that. Are any of you graduating this term? 1? Okay. You have to have your final to me by Tuesday morning. Tuesday morning. I said Wednesday before, but I found out since then they want grades in for graduates in by noon on Tuesday. So I have to have yours in by first thing, 8 o'clock Tuesday morning. This is not this coming Tuesday, the following Tuesday. Okay? Wait. No, it's 1 week from today. Okay. Okay, that's when you have to have it. The rest of you who are not graduating, is that right? Okay. You have to have yours in try to get it in to me by the end of business on Thursday. And I'm here until, I don't know what time, usually here until 7:45 on Thursday. I may leave a little earlier if I don't have anything going on. But get it to me. And here's the deal with that. We have graduation, and you have graduation. Are you walking? Okay. On Friday morning. What time?
On the invitation said 1.
I'm sorry.
It's on the invitation at 1. I don't know.
Oh, at 1. Okay. Oh, okay. That's good. I was thinking it was in the morning.
Okay.
Okay.
So typically, I got the invitations
At
at 1.
1.
Yes.
Okay. So that means I probably will come to campus Friday morning. So if you have turned it in by Friday morning, then I can get things graded then. But I have to leave. Did they tell you when you need to be there?
No, they didn't. We gotta wait till.
What's that?
They wait till rehearsal. I guess they can tell you rehearsal.
Oh, you haven't been to rehearsal yet.
It's on the 12th.
Oh, okay. My guess is you're going to need to be there by noon anyway. So that probably means they want us there by noon. So I'm going to have to leave here by 11:30. So if I could have all your work in by 11:30 on Friday, that would be ideal before I have to leave to go to the Birmingham campus. The rest of you, your grades aren't due until Monday at noon, but I want all the work in before I leave on Friday so I can get it graded over the weekend. So I probably won't be coming back to this campus after graduation. I'll just go home for that. Because I'm here until 7:45 at night on Tuesday and Thursday. Actually closer to 8 o'clock usually. So anyway, any questions about our timelines? Okay, let's do the vocabulary top of page 425. You can use a blank, blank, blank to represent a quantity that involves both magnitude and direction. A blank, blank, blank. Okay, I can think of the last word, but I don't know what they're meaning by the first 2 words. Oh, I know what they mean. And it's not vector. What's another name for a vector? A blank, blank, blank. The middle word is line. Okay, a line that has a fixed magnitude is a segment, line segment. And to have a direction would be a directed line segment. Okay, that's what they're looking for. It's sort of mystery meat here. Okay, you can use a directed line segment to represent a quantity that involves both magnitude, that's the line segment part, and direction, that's the directed part. Number 2, the directed line segment, PQ, has blank point P and blank point Q. What is point P called? Second? No, that's Q. So, so P would be initial. Initial point P. And you can look at the symbol almost and tell that. P is at the beginning of it, and Q is at the end of it. So P is the initial point, and Q is the terminal point. Number 3, the set of all directed line segments that are equivalent to a given directed line segment PQ is a blank V in the plane. And that's the word I've been wanting to use all along. Look at the title of this section. Vector in the plane. Okay, number 4. 2 vectors are equivalent when they have the same blank and the same blank. Magnitude and direction. Perfect. Okay. Number 5. The directed line segment whose initial point is the origin is in blank blank. Like these we drew here. We have both of these from the origin. So we say both of these are in blank blank. Second? No, that would mean magnitude 1. Standard position. They're in standard position when the initial point is the origin. Okay? Number 6. A vector that has magnitude 1 is the blank blank, is a blank blank unit vector. And number 7, the 2 basic vector operations are scalar blank and vector blank. 2 of your 4 basic math operations. Scalar blank and vector blank. What you do when you a vector, scalar multiplication and vector blank. Addition. Perfect. Number 8. The vector sum V1I and V2J is a blank blank of the vectors I and J, and the vectors V1 and V2 are the blank and blank components of V, respectively. Yeah, a lot of blanks there. The vector sum V1I plus V2J is a blank blank of the vectors I and J. Okay? Top of page 421. Examples. Bottom of page 420 is where they define it. Bold type. Very next to the bottom line. Anybody? Says right there, the vector sum V1I plus V2J is a blank blank of the vectors I and J. Same thing we have there.
Direction angle?
No, linear combination, very bottom of the page. Second from the last line. You see it? Oh, I don't know. I don't know how it looks on the ebook. So, okay. So linear combination of the vectors I and J, and the scalars V1 and V2 are the blank and blank components of V.
X and Y?
That's the only thing I could figure. They don't really have that one specifically in the book. I would say the X and Y components, or the horizontal and vertical. There's several things you could say. All right, that was easy enough, wasn't it? Okay. Homework exercises due number 9. It's on at calcchat.com. and then do either 11 or 13. They're both at calcchat.com. 11's at calcview. Do 15 or 17. They're both at calcchat. Then do any of the odds 19 to 23. They're at calcchat. 19's at calcview. Do any of the odds 25 to 29. They're all at calcchat. Do any of the odds 31 to 35. They're all at calcchat. 31's at calcview. Do either 37 or 39. They're both at calcchat. 37's at calcview. Do any of the odds 41 to 45. They're all at calcchat. 43's at calcview. Do either 47 or 49. They're both at calcchat. 47's at calcview. Do either 51 or 53. They're both at calcchat. 51's at calcview. Do any of the odds 55 to 59. They're all at calcchat. 57's at calcview. Do either 61 or 63. They're both at calcchat. 61's at calcview. Do any of the odds 65 to 69. They're all at calcchat. 67's at calcview. Do 71. It's a calcchat. 73. It's a calcchat. 75. It's a calcchat. And then any of the odds 77 through 87, they're all at calcchat. Then do either 89 or 91, they're both at calcchat. And then do any of the odds, well, do 93, it's at calcchat. True, false, either 95 or 97, they both should be at calcchat. And then there's an error analysis. I really don't care for them too much, but you can do it if you'd like. Number 99, there's a proof that's 101. 103 is one that you should be able to do. And 105 is a graphical reasoning if you're interested, and 107 is a writing exercise if you're interested in that. So let's get out of this. Any questions before I clear my ink? Okay. So let's go back to the beginning of 6.4. Okay. Chapter 6, again, is additional topics in trigonometry, and 6.4 are vectors and dot products. Okay. Now, we've already talked about one type of multiplication of a vector. Take a scalar and multiply it by a vector. You either increase the length of the vector, decrease the length of the vector, or reverse the direction of the vector, increasing or decreasing its length. Some combination of those. Okay? Are we almost out of time? No, we got 10 minutes at least, don't we? Okay. All right. Well, we're going to talk about two other types of vector multiplication. Or at least I think we will. I don't see why we don't. Nope, I guess we're not. I'll try to mention the second one, or the third one. We're going to first talk about dot products. Okay? So we'll find the dot product of two vectors and use the properties of the dot product. First, we've got to define what that is. We'll find the angle between two vectors to determine whether the two vectors are orthogonal, meaning perpendicular, meaning at right angles. All those mean the same thing. Another one is normal to each other. That means the same thing. We'll write a vector as a sum of two vector components, as we have already done, but we'll give it maybe a little new twist. And we'll use vectors to find the work done by force, which frankly will be using a dot product. So what do we mean by a dot product? Well, if you remember in algebra, early on, I bet you used what is a multiplication sign? An X, okay? But then after a while, when you got into algebra, you probably quit using the X as a multiplication sign. Why?
Because you use X
as a variable, and then it would be confusing. Is that an X or is it a multiplication sign? So then we started using a center dot sometimes. But we had other conventions too, like writing a number next to a parentheses, that meant multiply. Writing a number next to a variable, that meant multiply. So we had several ways to multiply. We're going to take these two right now only one, that dot. And we're going to define that dot in vector multiplication to be a very specific type of multiplication. Okay? So in this section, we will study a third vector operation called the dot product. This operation yields a scalar. You start with two vectors, and when you dot them together, multiply them together with a dot product, you get a scalar. Now that wasn't the same as the scalar multiplication. You multiply a scalar times a vector, you get a vector. Okay? Now we multiply a vector by a vector and get a scalar. So it's a little bizarre. So here's how we define the dot product of two vectors. Now these are two-dimensional vectors. U is U1, U2 in component notation. V is V1, V2 in component notation. Okay? The dot product of these two would be multiply the first components together, U1, V1, and add to that the product of your second components, U2 times V2. And that, because these are scalars, and addition's a scalar, multiplication's scalar, you get a scalar answer. That is a dot product. Okay? And if you had three-dimensional vectors or 17-dimensional vectors, you do the same thing. Multiply the components, corresponding components together and add the sums. Add the products, I guess. All right. So here are some of the properties of a dot product. Okay? U, V, and W are all vectors in the plane. That means two-dimensional vectors. Or in space, that would mean three-dimensional vectors. And then C would be a scalar quantity. Just a number. So, if you had the dot product of U dot V, that's exactly the same as V dot U. And if you think about it, it makes perfect sense. Because this would be U1 V1 plus U2 V2 if it's in the plane. And this would be V1 U1 plus V2 U2. Multiplication is commutative in scalars, is commutative in dot products. Okay. Here's another property. The zero vector dotted with any vector V is going to be the scalar number 0. Okay? This is the scalar vector, the zero vector, that's the number 0, the scalar 0. And of course that makes sense too. Again, if we're in two dimensions, this is 0, 0 times V1, V2, that's 0 times V1, which is 0, plus 0 times V2, which is 0, and 0 plus 0 is 0. So certainly that gives you 0, nothing. Okay. Number 3, if you dot a vector with the sum of two other vectors, then that's the same as the dot of these two vectors added to the dot of those two vectors. It's sort of a distributive property of dot products over vector addition. Okay? If you had to give it a name, that would be it. And that makes perfect sense because the sum of two vectors is a vector. You dot a vector with a vector, you get a scalar. Where you dot a vector with a vector, you get a scalar plus a scalar is a scalar. So that makes sense. And number 4, if you dot the same vector with itself, you get its magnitude squared. Well, let's see. That would be V1 times V1 plus V2 times V2. That's V1 squared plus V2 squared. Well, that would be exactly the square of the magnitude of the vector. Yes, that makes sense. And then finally, if you distribute a scalar multiplication, this is bizarre, across a dot product, you can write it that way, or CU dotted with V, or U dotted with CV. It doesn't matter. Just use the scalar once and multiply either by the dot product, by one vector then dot product, or the other vector and then dot product. Either way. That's not really a distributor. It's, I don't know what to call it. Kind of an associative property, but not quite. It doesn't fit the bill for that. But it sort of makes sense. It does make sense. So let's do example 1. Okay? What's the dot product of these two vectors? 4, 5 dotted with 2, 3. Oh, man. How did they do this? Okay. What would that be? 5 dotted with 2, 3. Those are components of two vectors. Help me. Anybody?
So it would be 8
8
and 15,
plus 15, which is
23.
23. Perfect. 4 times 2 plus 5 times 3, which is 8 plus 15, which is 23. A scalar number, okay? A number. So a dot product always produces a scalar. Okay. Let's do the B one. Okay? What would that be? 2, negative 1 dotted with 1, 2.
2 plus the 2 minus
Again,
2 minus 2,
which is
0.
0. Now that means something, okay? We aren't quite prepared to say what it means yet, but let me suggest it to you. Let's visualize 2, 1, or 2, negative 1. That would be 2 on the horizontal axis, down 1. Okay, there's that vector. See it? Okay, let's do 1, 2. 1 and up 2. What do these look like anyway? They might be relative to each other. 90 degrees. You'll find out later that's exactly true. Anytime you've got two vectors together and they come out 0, you know they're perpendicular or orthogonal or normal. They have various names they can call it. Okay, let's do this one. 0, 3 dotted with 4, negative 2. What would that be? Anybody? Negative 6. Perfect. So if it's 0 times 4 is 0. 2 times negative 3 is negative 6. 0 plus negative 6 should be negative 6. Perfect. Is there a fourth one? No. Just those 3. Okay. How are we doing on time? 1 minute. Okay, there is a checkpoint there. Please do your checkpoint. It looks like next time we will need to begin at example 2 before we get to angle between two vectors. Okay? So we'll begin with the top of page 430. Homework exercises, I think you can do any of the odds 7 through 11. They're all at Calc Chat. Calc Chat. 7's at Calc View. And try doing 13 through 21. They're all at Calc Chat. 21's at Calc View. And we'll hold off on the rest of them. Though I think you could do 23 to 27. We'll hold off on that until later. Okay. No, I'd say let's go ahead and do that. Do any of the odds 23 to 27, and they're all at, they're all at Calc Chat. Good deal. Any questions? All right. So get everything finished and into me by Thursday morning. Okay? Good deal. I'm sorry? Okay, I couldn't hear what you said.
I don't know if I'm on the right track for the paper.
Okay, what are you what do you mean?
Like, can you read to see if I'm on the right track or anything, or if this is like what you want me to talk about?
No, I mean that looks good to me.
Oh, okay, cool. Because
Yeah.
I was talking about discount prices and stuff,
Right.
and how it that affects
Sure.
accounting, and taxes. So I didn't
Right.
know if that's what
Okay,
you want or you
that's
actually want to talk
perfectly fine.
about. Okay, thank you.
Good deal. Thank you.
You have a good one.
All right, you too.